Okay, remember that light or an electromagnetic wave is a transverse wave with the electrical field oscillating in one direction, the magnetic field oscillating in the perpendicular direction, and the wave propagating or traveling in the perpendicular direction to both E and B. Again, so that's a transverse wave. Now we define something new with what we call polarization. What we define as polarization is the direction along which the electrical field is oscillating. In this particular case, for example, in this graphic, the electrical field is oscillating along the y-axis. So our direction of polarization for this wave is the y-axis. Okay, for electromagnetic waves, there are different types of polarization. What we call linear polarization. Linear polarization is polarization when, for that particular wave, the electrical field oscillates along one unique direction, a direction that does not change. Now, for example, in the simulation that we have here, the electrical field, this electromagnetic wave has a polarization along the z-axis, and that polarization does not change. That's what we are saying here. Now, there is what we call circular polarization. This one is kind of neat to look at, but it is a particular case where the polarization of E changes. And I'm going to try to show you one here. Okay, I pulled in the simulation the way it comes up, but let me just pull out these things, move them away. Okay, so let's move this all the way to the other side, move this to the other side, and then move this to the other side as well. So this one, for example, you notice here, the electrical field, the tip of the electrical field is going around in a circle. That's why we call it circular polarization. What happens when you have a phase difference between one component of the electrical field like EX and the other component EZ, when the phase difference between them is 90 degrees, it's kind of rotates, and that's what we have here. That's what we call circular polarization. And unpolarized. I don't have a simulation here that shows you that. Actually, I have a simulation that does not run very well on this computer, but most light is unpolarized or have polarization that changes randomly. The electrical field can be oscillating parallel to the x-axis in one instant, parallel to the z in another, parallel to the y in another, and so on. That's a random polarization or unpolarized light. Okay, so again, linear polarization, the direction of oscillation of the electrical field is constant. If we go back again to that simulation, the way we can get that is, for example, we remove this. So this is a constant simulation, but to make it more visible, I'm going to restrict it to one direction, and I'm going to make it slightly larger so we can see it. So you see here the electrical field is oscillating along one unique direction. Okay. Now, I'm not showing the magnetic field here, but I can show it if I want to. It is going to oscillate in the perpendicular direction. Okay, but that's a unique and changing direction of the electrical field. That's the key. So in this particular case, the polarization of the wave is along the x-axis, since E is oscillating along the x-axis. That's linear polarization. Circular polarization is what I showed you just a few instances ago, but I'll do it again. So I'm going to have another component of the magnetic field. I'm going to have them equal to each other, and then I'm going to have a phase difference between them at 90. Okay, and there you see it in all its glory. See why we call it circular. The tip of the electrical field is kind of forming a circle. Now if we have the magnetic field showing too, the tip of the magnetic field is also going to be going around in a circle, but that circle is going to be, so you see it differently. Isn't that quite neat? Okay, beautiful, I think. Now, we have what we call a polarizer. A polarizer is going to be usually a piece of material that has some molecules in it, such that it has a preferred axis. The molecules are not the same, are not arranged the same way along one direction than the perpendicular direction. A polarizer, because of that, is going to have what we call a transmission axis. Along the transmission axis, if the electric field is parallel to the transmission axis, light is going to be transmitted unaffected by the polarizer. However, if the electric field is perpendicular to the transmission axis, then the polarizer is going to block it. So what does that mean? Okay, let's pull in the simulation again that we were just looking at. Let me remove B. So we have circular polarization here. Okay, and this is what we are talking about. So the electrical field in this case is changing direction between X and Z. But then when we have a linear polarizer and the transmission axis here is along the along the x-axis, now you notice the transmitted wave is just along the x-axis. So it's going to cut out whatever is not along the x-axis. Let me illustrate that some other way. Let's remove the circular polarization. So I'm going to have an electrical field that's along the x, meaning that the wave is polarized at a direction parallel to the transmission axis. So you notice there, the polarizer does not affect the wave. Now, if the wave is polarized perpendicular to the transmission axis of the polarizer, it is totally blocked. Now, of course, if it is polarized such that it has a particular angle relative to the transmission axis, only the part, the component that is parallel to the transmission axis is going to be transmitted. Okay? That's an important point. Now, one thing is important when we talk about this, how much of the light is going to be transmitted. And usually in talking about that, we talk about the intensity of the light. To talk about intensity, we have to define it. Definition of intensity is power per unit area, or power over area. We use two symbols sometimes to represent it. We use I or S, and it is power over area. Just one thing to note here, the intensity is proportional to the amplitude of the electrical field squared. And then if you remember that E is actually proportional to B, there is a direct relationship between them. The direct relationship involves just C. Now, because of that, we can say that it is also proportional to the amplitude squared of the magnetic field. So that's important. It's power per unit area. It is proportional to the amplitude of the electrical field squared, or the amplitude of the magnetic field squared. Now, an ideal polarizer is going to take unpolarized light polarized in all directions, and it's going to cut it in 1/2. A polarizing material is going to result in light being transmitted at half the intensity of the unpolarized incoming light. Okay, this is under ideal conditions. Now, in real life, there will be some different losses in the polarizing material. The different losses, kind of absorption type kind of losses. Now, when you think of half, why is it half? Because when you look at all possible directions, whatever is parallel to the transmission axis is going to move through. Whatever is perpendicular is going to be blocked. Whatever is in between is going to have the component, think of it as a vector, the component that is parallel to the transmission axis transmitted, the component perpendicular to the transmission axis blocked. So again, the power outside the transmitter, the polarizing material, is going to be half of the power coming in. Now, if our light is already polarized and we subject it to a polarizer, so in this case we have light polarized in this direction, the red arrow here. And if the polarization axis makes an angle theta with the transmission axis, now what's going to happen is the part that's parallel to the transmitted axis is going to be able to go through. The part that's perpendicular is going to be blocked and absorbed. Now, again, thinking about vectors, the transmitted part is just equal to the overall amplitude of the electrical field times the cosine of the angle, the adjacent one. Remembering that the intensity, I'm writing it as I or S, is proportional to E squared. So what does that mean? That means that actually the transmitted intensity is going to be proportional to the cosine squared of the angle between the direction of polarization of the field and the transmission axis. So I transmitted is going to be I incident cosine squared of theta. Special case, if my angle is 45 degrees, cosine is square root of 2 over 2, so I get 1/2 here, so I get half the light. Now, if my angle is 90 degrees, cosine is 0, that gives me no transmitted light. Now, this expression I transmitted is equal to I incident times cosine squared of theta is called the law of Malus, or Malus's law.